All right, number 4, we got all kinds of good stuff in this problem. Gives us a diagram, some information about a cylinder, the HDT. First question is, what is the rate of change in the volume of the barrel with respect to time when the height is 4? So I know that h is 4. I also know the rate of change in the height is this formula that's in the problem. And the question is the rate of change in the volume. So I need the volume of a cylinder here. We should know that that's pi r squared h. A lot of times we have to find a relationship between r and h, but in a cylinder, the radius never changes. So I can actually substitute that because this is always going to be 1. And so I really just have v equals pi h. And this is a related rate problem, and so I'm going to take the derivative, and I get this. And the rate of change in volume, which is what the question is just going to be pi times dh dt, which is negative 1/10, times the square root of h, where in this problem is 4. And so you end up with pi, this is times negative 2/10, which is 1/5, so negative pi over 5 is my answer. It does ask for units, which it will a lot of times in a related rate problem. This is a volume unit, so that's cubic feet, over a time unit, which is seconds. So negative pi over 5 cubic feet per second is our answer to part A. All right, part B gives us a different snapshot in time. When h equals 3, find the rate of change of the height of the water with respect, is the rate of change increasing or decreasing? So it's actually asking us about the change in the rate of change. So you have to read that carefully, but is the rate of change increasing or decreasing is actually a question about the second derivative. So I'm going to write an expression for the second derivative. That's going to be negative 1/10. And then the square root of h is going to be 1 over 2 root h. And I need a dh dt here. And let's go ahead and replace dh dt with its formula, which is negative 1/10 square root of h. So it actually ends up that these square root of h's cancel, these negative signs cancel, and you get positive 1 over 200. So the fact that d squared dh dt is greater than 0, notice we didn't even have to use the h equals 3. It's always going to be greater than 0. Means that the rate at which the water is changing has a positive rate. So that means that it's going to be increasing. So dh dt is increasing, right? Because its derivative is positive. All right, part C is a separation of variables problem. Remember, these are the ones that people can miss a lot of points on if they don't start correctly. They give us a height at 0, so that's an initial condition that we're going to use. But it actually tells us specifically to use separation of variables. So I'm going to take my dh dt formula. I'm going to split up the variables, so I have all my h's on one side. This is going to be h to the negative 1/2. When you move it to the left, you have a choice of moving this 1/10, but it's actually easier to not move it. And then I'm going to simply integrate each part. So I have this integral, which is h to the positive 1/2 with a 2 out in front. And then I have this antiderivative, which is negative t over 10. Don't forget your plus c here. I'm going to go ahead and solve for h first. You could also figure out the c now. I'm going to do it later. So I'm going to divide everything by 2. H to the 1/2 is negative t over 20. Plus, and then c over 2 is still just c. We can leave it like that. And then I'm going to square both sides. So when I take negative t over 20 plus c and you square it, that's my general solution. Remember that h of 0 equals 5, and that's going to equal c squared. And so c ends up being the square root of 5. And so my final answer is then going to be h of t equals negative t over 20 plus the square root of 5 squared. And that is my final answer for part C.